It's my pleasure to introduce Yizhe. He is an assistant professor at the University of Southern California, and he got his PhD 3 years ago from University of California, San Diego, and then he had a research position at Irvine, and also a position on deep learning financed by Simon's Foundation. And right now he is at the university, at the Mita Kleffler Institute in Stockholm. He is interested in probability and combinatorics and the applications to data analysis. In particular, he works on graphs, random matrices, random tensors, as well as community detection, neural networks, and differential privacy. His main results concern the spectral properties of sparse random matrices and analysis of spectral clustering algorithms. He has already he has published already 22 papers, and after PhD he gave talks at more than 30 conferences. He will organize a session random matrices, related structures and applications at the meeting of American Mathematical Society in the fall this year. So it's remarkable, all this is very remarkable as for this stage of career. Alors, please.
Thank you, Eva, for the very kind introduction. So I'm still in Los Angeles right now. So I'm going to Mita Kleffler this weekend. So it's very nice to speak at this workshop. Can you hear me?
Yes.
Is everything good? Okay, yes. So I gave so the organizer would like me to talk about something relevant to random matrix theory and deep learning. It's a big topic, so I want to focus on a very specific phenomenon that has attracted a lot of interest in the recent 5 years. It's called the double descent phenomenon. So we will briefly talk about this phenomenon, why is it interesting, and what's the relation to random matrix theory, and what can we study in mathematically. So let me start with a general framework of machine learning. One particular type of machine learning is called supervised learning. So I give you an example of classifying pictures of cats and dogs. The goal of this for this machine learning task is you want to build a model that could distinguish between images of cats and dogs. And usually there is a training step. It's similar to when you go to the school, you need to do some practice exams. You do some quizzes where you answer the question and the teacher gives you a true answer, and you can compare and see what mistake you have made. So for this training data, it's like your exercise. You give a lot of pictures of cats and dogs with the correct label, and you feed this data to a machine. This machine can use this data to train some of these model parameters to make very small mistakes on those training data sets. So you make very few mistakes on those exercises. And then after that, we want to test how smart is this model. Then you can give them new pictures without telling them whether it is a cat or dog. And you ask the model to give you a guess. Okay, so interestingly, I just write down this description and send it to ChatGPT. And I asked GPT to give me a picture to illustrate this concept. And you see on the right-hand side is the artwork from ChatGPT. There are mistakes, right? The spelling is wrong, and uh, many characters, these letters are not well written, but it gives you a sort of concept. So you can see the current technology, how smart they are doing tasks that we couldn't imagine several years ago. Okay. So this is a big framework. And then the question is, what is the model you are using to do this task? And one particularly popular model in many application is this neural network. So let's start to mathematically define a neural network. In one sentence, it's just a function with some parameter theta that takes the input to a value. So in our previous example, the input could be the image. The image you can imagine as a matrix with pixel, but I can also imagine it's a high dimensional vector. So you fit the model with a vector, and the output's a number in real number. It could be 0 or 1, or you could be something between 0 and 1. The probability that it's a cat or dog. So it's a number. And how do you get this function? It's a composition of many layers. So when you take the vector in, this vector is multiplied by a weight matrix, and it passes through some nonlinear function. Then you go to another layer and multiply by a matrix and another activation function, and so on. So in this case, you see your input is a three-dimensional vector. And after you multiply by a matrix of a dimension 4 by 3, yes, then you get a new vector of dimension 4, but then you apply some nonlinear transformation. Then you keep going and going. At the end, the last layer, you have four point, but then I can aggregate, I can sum over all the vertex with some weight to get the last output. So it's just a composition of matrix times a vector and with an activation function. What's the choice of activation function? You could have some nonlinear function like absolute value, and the popular one is like ReLU, which ignore the negative part. You just output 0 if the value is negative, or x itself if it is positive, and some other nonlinear function. So the important feature of this neural network is that you have a composition of matrix vector multiplications, and you pass by a nonlinear function. Okay. The important thing here is this nonlinearity. Otherwise, if I remove this nonlinear part, it's just a matrix times another matrix and another matrix. So overall, it's still a matrix times a vector. When we have a matrix multiplied by a vector, it's just some linear combination of this vector. So this is not rich enough to express many different function behavior. That's why this nonlinearity make it very powerful. And the goal, like before, you give this model a set of training data, which xi could be the images and yi could be the label, whether it's a cat or dog. And you fit this data into this neural network. The challenge here is there are not a lot of parameters to choose. Right? We need to make this model smart enough to make few mistakes on the training samples. And if you give you a new image, it could be a good prediction. So the challenge is to find the parameters to make this function smart. Okay. And you see the parameter lives in a very high dimensional space because I need to pick this output layer, which is a vector, and in different layers, there are many matrices you need to pick. So it's a high dimensional challenge to get those parameters chosen. Okay. And we haven't talked about what is the principle to choose those parameters. How do you update those parameters based on the training data you see? Okay, so but this is a general picture. In one sentence, neural network is just a nonlinear function defined by matrix times a vector by another nonlinear function and so on. And you pass it to many layers. Okay. So what are the important questions you can ask for this type of architecture? So the central question here is, how do you find the best parameter, right? How can we tune so many parameters to make it perform very well on new test data? A general principle is you define sort of loss function on the training set. So the loss, you can think about a penalty if you make any mistake on the training set. If you answer a question wrong, you lose some score. Right? So this loss function is keeping track of the performance of your training samples. And you can update this data, this model parameter, by doing some minimization problem on this loss function. So we want to make as few mistakes as possible on those practice problems. And this is a problem about optimization theory. So you take some derivative, you minimize this loss, and you update this parameter theta by when you see more examples and you keep updating the weight to make as few mistakes as possible on the training set. So
Sorry,
this is something we will not enter today. It's a quite active area. It's about optimization theory.
excuse me, may I have a question?
Sure.
So what are yi here?
Yi is so in my previous example, you can imagine yi is whether it's a cat or dog. So it could be 0 or 1.
So possible answers, yes?
Yes, possible answers.
Okay, thank you.
Yes. And another question we can ask is, yes, we have a composition of different layers. And by changing those weight, this function could express the very different behaviors. And we can ask how many functions, what is the class of the function you can express by neural networks. This is a problem about approximation theory. So we have some classical result in real analysis. For example, in a bounded continuous function can be approximated by polynomials. So you can ask a similar question if you have some continuous function, what is the type of function you can be approached by this neural network? Right? What's the and this is also a relevant question, like related to analysis. And today we will focus on a more probabilistic and statistic question. So it's about test and generalization error. So yes, you can train this neural network to make very few mistakes on those on the examples you gave. And we care about the performance on this unseen data. If I give you a new picture of cats and dogs, how likely you can classify it correctly. So this is the problem about generalization. Okay, so today we will focus on some recent mathematical development, trying to quantify and understand the test error in this neural network architecture. We're not being very ambitious. We'll start from some very simple model, and I will introduce some recent development. So why this is interesting to study the test error of neural network? So let's start with some classical wisdom, classical textbook examples about how do you pick a model to fit data, right? Essentially, what we are doing is you want to pick a model so that you make very few mistakes on those data point. Okay, so we give a task of curve fitting. Here, you take some samples of this form. It's a two-dimensional point on the plane where x is a x-axis and the y-axis is given by a polynomial and plus some observation noise. So it's a very common situation when you measure some location of the point, you have some measurement error. So the true data lies on degree 3 polynomial on a curve, but you could have some perturbation, noise. Okay, so this is the sample you get. And the task is to fit, you want to find a curve that passes through many points and to make few mistakes on the unsynced data. Okay. So if we want to do it only with linear function, you have so many points. I want to find a linear function that fits all the points. It's a challenging task. You might want to just find a line that across the average position of the point like this. And you see, you cannot fit the data very well. The reason is the model is too simple. We're only looking for a line that's passed through all the point. There's no enough degree of freedom to just go through all the point, right? And this is a situation where we cannot use a linear function to explain the relation of those data points. There is a degree 3 polynomial relation, but you are only using a simple model to fit. That creates something called a bias, so you cannot fully explain the relation in your data. And another extreme situation is I pick the wrong degree. If I just look for a degree 20 polynomial to pass through all the point, yes, it's doable because there are only those many points, and you can find a polynomial to exactly pass through all the point. But that creates a big fluctuation, a big variance. And the issue is when you slightly change those location of the point, you can see this degree 20 curve will change dramatically. Right? They are very sensitive to the noise from this data. So although it fits all the noisy training point, it's very sensitive. And you can imagine if I give you a new sample like this from the curve, for example, if I pick a point here, and that's very far from the curve you are trying to draw, right? So yes, you make no mistakes on the original on the existing point, but this is a bad model to predict what could be the next point on this curve. Okay, so you see there's a trade-off. If the model is too simple, you are underfitting. You cannot explain the relation in your data. If you are creating a very complicated model to explain this relation on your data, it could be that you perform very bad on new data point. So this is called a classical trade-off between bias and variance. Okay, so so we already see if the model is simple, you could have a big bias. You cannot fully explain the model. And when the model gets more complicated, this bias could decrease because I can just have a more complicated curve to fit everything. And the variance will increase because it's sensitive to noise if your model is too complicated. So there is a trade-off. It suggests that if I consider both the variance and the bias, we should look for something around a sweet spot that has a relatively low variance and a relatively low bias, so that it fully capture this behavior of your noisy data. So this is also, again, an example where if you have a very straight line, it's underfit, and if you get the right curve, it gets a best accuracy to explain the data. Otherwise, if you have a very curvy curve, it's not good for prediction. Okay, so this is a very classical picture you learn in basic statistics theory. But this is the puzzle because if you have this kind of picture, it fails to capture what's happening for neural network. As we already explained, this model is very complicated. You have so many parameters, different depths, and this nonlinear function. When you consider this model complexity, it's a very complicated model. But however, it has very low generalization error. And in this very recent architecture, for example, we're using ChatGPT, the number of parameter is like more than a billion, right? You have so many parameters, and the data is much smaller. The amount of data you use is much smaller than the parameters. So when you look at this kind of program, it doesn't explain what's happening in your network. The generalization error is actually very low because many times you can use ChatGPT to or other model to or like facial recognition. It makes very few mistakes. So this is a big puzzle that we can not use existing statistical theory to explain. And recently, it has been observed in many simulations, in many real neural networks. If you do this training process with a lot of parameters, it has this two different behavior. So when we say training error, it means how many mistakes you make on the training set. And you see when the model becomes more complicated, so the number of parameters increase, at some point you will make zero mistakes, right? Basically, this neural network is able to memorize cats and dogs with the correct label, so you can make zero mistakes. But still, when you increase the number of parameters, the mistakes is zero. And what we care about is the test error, right? So the test error first go down and up. This is similar to this classical picture we have before. It's a U-shaped behavior. There is some middle point where the model is not too complex, but explain the relation in your data. And it goes through a peak. And after the parameter gets more and more, the error goes down and down, and it keeps going down. At some point, it has a limit, but it's much better than what you have before. So when you increase the parameter, this model performance gets better, then worse, then gets better again. This is called the double descent behavior. And I give you another experiment figure from another paper where you observe similar thing. When you keep training the model with more parameters, the training error goes down, and at some point it becomes zero. But when the model becomes more and more complex, you see this double descent curve. The error goes down and up, and eventually it goes down. And when you have more parameters, you see the end point of this curve is still better than this U-shaped curve when you have fewer parameters. So it has a non-monotone behavior, but eventually this performance on the test data becomes better. Okay, so this is a puzzle that's not explained by the previous picture about this bias variance trade-off. So this is quite of a big challenge for theoretical computer scientists and mathematicians, probably the statistician, to understand what's going on. And around 2019, the theoretical understanding of this double descent phenomenon has emerged. There are several groups propose theories for explaining this phenomenon. So I'm giving you a cartoon by a paper from Belkin. And what it explains that a common diagram in the modern machine learning is that as you increase the model capacity, you always have this kind of double descent curve where when the model is relatively simple, you have this classical regime. It's called the under-parameterized regime. The model is not able to make zero error on the training data, so you always have some training error. And the test error has this classical U shape. You go down and up. But after some critical point, when the model is big enough to make zero mistake on training data, then the test error goes down and behave much better than the previous situation. This is called the over-parameterized regime. Okay. This is a framework to say that many machine learning models will have this different shape called double descent shape. And what you can do in theory or in mathematics, you want to find a very simple model with a clear formula that could recover what you have in the experiment in practice. So this is the goal for our mathematician, that we want to find the simplest model to explain this non-trivial behavior and to have a rigorous analysis. And the conclusion after several years of work is that, in fact, this double descent curve is not a special feature of deep learning. It's a special feature of a high-dimensional model, but it can happen in high dimension with much simpler models, even with linear regression. So drawing the best line to fit curve, you will have this phenomenon. Okay, and the connection to what my research area is that, in fact, in explaining those models, random matrix theory has been one of the key players. Okay, so let me have a very quick introduction of random matrix theory in 2 slides. In one sentence, random matrix theory is an area to study eigenvalue and eigenvector behaviors of a large matrix with random entries. Okay, so we want to have a very big matrix where every entry is a random variable. And you can imagine if you want to study eigenvalues and eigenvector, it could be very complicated because you don't have a control over all the random variables, right? So instead of looking at individual eigenvalue, we can look at what is the distribution of all eigenvalues. So this is the first type of question you can ask in random matrix theory. So one of the very classical results is proved by the physicist Wigner around 1955. It tells you that if you have a very big matrix with a lot of random entries, in fact, in high dimension, the eigenvalue behavior is quite simple to describe. So let's define it very formally. If you have a matrix which is of size n by n, and we make sure the matrix is symmetric. So when you take the transpose of the matrix, the upper triangular entries and the lower triangular entries, they are the same. So the freedom of this random matrix will come in from the upper triangular part. If I define the upper triangular part, the lower triangular part will be defined already. So the upper triangular entries, if we just assume they are independent distributed random variable, each entry is a random variable with mean 0 and variance 1. So you can imagine it's just a standard normal distribution or Gaussian random variable with mean 0 variance 1, but it also works for many other distributions. And the key point here is you want to make this random matrix very large so that we take the size of the matrix to infinity, okay? And to make a minimum state, to make a reasonable statement, I need to normalize the matrix. Otherwise, the eigenvalue will grow. The size of the eigenvalue goes to infinity. So you need to divide this matrix entry by square root n, okay, so that all the eigenvalue stays inside an interval, okay? Then when we take n go to infinity, the eigenvalue distribution of this matrix will converge to a semicircular. This is one of the classical, or one of the important results in random matrix theory. And what do I mean by eigenvalue distribution converge? Intuitively speaking, you can imagine I draw a histogram to count how many eigenvalues are inside each tiny interval. Then that histogram basically is an eigenvalue distribution. But you can make it very precise using weak convergence of probability measure. But this picture explains what's happening. If you just draw the histogram of eigenvalue distribution, when the matrix gets larger and larger, this histogram will be closer and closer to the red curve. And this red curve is a density function of this semicircular. Okay. So as the matrix gets larger and larger, you can easily describe the eigenvalue distribution. It becomes something deterministic. It's very similar to law of large numbers phenomenon when we study probability. If you add in IID numbers and divide by n, it converges to the mean of this collections. So this is something similar to law of large numbers, but in the language of matrices. This is an important object to study statistical physics. If we want to describe a complex system with many randomness. Also, it's relevant to study random graphs. This some combinatorics object. You also see this semicircle law. And it's also important to model like a matrix with noise in signal processing, and where you have each entry is a noise, and when you put the noise into a matrix form, it gives you an eigenvalue behavior like this. So it's a very universal phenomenon across many areas, and it's a universal phenomenon with a very flexible choice of random variables. You don't need to know whether it's a Gaussian, it's a Bernoulli, or other variable. You just need to assume it's a mean zero variance. Okay, and another type of random matrix, more relevant to statistics or data analysis, is called sample covariance matrix. This is a class of random matrix that you want to describe for a large data set. And that's very relevant to this discussion we have today. So if we have a collection of random vectors in D dimension, we can just make each vector a row, and you put all the vector into a matrix form, right? Each row is a vector, you just put them together. Okay. And we can define a sample covariance matrix, which is the average of those rank 1 matrices. Each rank 1 matrix is the random vector times the vector transpose. This is a D by D matrix, and you sum all the D by D matrix and you take an average. This is called a sample covariance matrix. And there's another classical result to describe the eigenvalue distribution of the sample covariance matrix. Okay. Here we have a D by N matrix, and we make the simplest case where this each random vector has independent entries in. So each entry are independent, identically distributed random variables, similar as before. You assume it's a mean 0 and a variance 1. And now here we have two parameters, an n and a d. N is the size of the data set. D is how large is the dimension of each vector. If we assume they both go to infinity, but at a comparable rate, so n and d goes to infinite, but the ratio d over n converges to a constant. Okay, then this eigenvalue distribution will converge to a probability measure. The density is given by some explicit expression. Okay, and there is a difference between gamma greater than 1 and gamma between 0 and 1. When gamma is greater than 1, you have some mass at a 0. So this matrix has many 0 eigenvalues. And you can see here, because I have X transpose X, the rank of this matrix is the minimum of D and N. So this is actually a D by D matrix, and if the gamma is greater than 1, you will have you'll have a 0 mass as a 0, because the rank is not D. Okay, maybe I made a mistake here. So in one, it depends on how do you define aspect ratio. Yes, and then in one example I give you here, you pick some gamma that's not giving you the 0 as 0 mass. Then the histogram of the eigenvalue will lies in a positive interval, and then close to a shape that describes by this this function density here. Okay, so it has a boundary, gamma minus and gamma plus, and you have a shape described by this curve. One thing to check is this matrix is positive semi-definite, so you don't have negative eigenvalues. In the Wigner case, I have positive and negative eigenvalues, and in this case, this matrix gives you only positive eigenvalues. Okay. So those are two classical model for random matrices. And the key point is it's a very general model. You don't need to know the specific distribution, and you need to take this parameter large, go to infinite. And for Marchenko-Pastel distribution, I need the dimension and the size goes to infinite simultaneously with certain rate. Okay, so with that in mind, we will study something very simple. It's about a linear regression, but we will look at linear regression in high dimensions. And in this model, we'll see you can see this double descending curve, and it can be explained by random matrix theory. So what is our model here? Again, we have a collection of training data where xi is the d-dimensional vector, and each yi is the label or value. You can still use this picture and label example, but it could be a general collection of data. You have d-dimensional vector, and one for each data you give a value to it. And this, we assume those data come from a linear model. What does that mean? You have some unknown coefficient beta 0, which is also random. Okay, it's a Gaussian vector in d dimension, and this label is generated by your training data inner product with this d-dimensional vector plus some noise. Okay. So in one dimension, that basically means you have a straight line, but the data is perturbed by some noise. But we can generalize this two-dimensional picture to a d-dimension. Then you have some coefficient with d-dimension, and the answer is given by inner product between the x vector with the coefficient. And those data xi are also just random vectors with distribution Gaussian. It's a d-dimensional Gaussian vector. Okay, so we're not making any difficult assumptions. We just make sure everything is Gaussian with the nice distribution, and everything behaves similarly. With there's no different covariance structure. It's just identity covariance. That means every coordinate of these vectors are independent. Okay, so the noise is also Gaussian, but with a variance sigma square. Okay, so this is the model we have. And what is the training step? The training step is, yes, we want to find the best coefficient, a d-dimensional coefficient that explain the training data. So we want to find the beta here that makes as few mistakes as possible, right? Yi minus this prediction is the mistake, the error you make from the model with coefficient beta. And we want to pick the best beta that has a small error on the training samples, okay? This is a training error we have that depends on beta. Okay, is that clear? And what is the relation to random matrix theory? We can just put everything into a matrix form. So each label of the data point, we can put them in a vector form. That's an n-dimensional vector. And I can write a random matrix where each row is my xi. Then it gives you an n by d random matrix, and each entry is a Gaussian random variable. Okay. So we just make it very simple. Every entry is a Gaussian, but you can also consider the case we don't give you a specific distribution. You can assume it's mean 0 and variance 1, and the similar story can also be described. But let's make it simple. And because all the entry has a continuous distribution, we can actually check the rank of this random matrix will be the minimum of n and d. So it will be a 4-rank matrix. All these vectors will not have a linear relation between them. Okay. And now here comes a linear algebra question. We want to ask, what is the situation where the training error could be 0? Right? Can I find a beta that make no mistakes on these training samples? Equivalently, you ask the question, is it possible to find a beta such that this matrix X times beta exactly equals the label Y? This is actually a familiar concept when we learn linear algebra. It's about solving linear system. Right? Is it possible to find a solution that satisfies this linear system? Right? So we have something already learned in linear algebra. If this matrix is n by n, right? This X matrix is n by n, we know the rank will be n, then it's a 4-rank matrix. You could solve the unique solution by taking the inverse of X. Right? So the unique solution will be X inverse Y. Okay. On the other hand, if D is greater than N, what does that mean? I have D unknown variables to solve, but there are only N equations. So you could have infinitely many solutions to solve this equation. Right? But on the other hand, if D is less than N, that means I have D variable, but I have more equation than number of variables. And in this case, there is no solution to make this, this happen. But we can ask, how do we minimize the loss? And from linear algebra, you know there is a unique beta hat to minimize this loss, y minus x beta. And how do we get this beta hat? I'm just drawing you a picture that you might see from linear algebra, right? This x times beta lives in the span of the column vector. So it is a column space. When you choose a different beta, they all live in the column space. And whether we can find the beta that satisfies this equation depends on whether this vector y is inside this column space of x. Okay? If d is less than n, you don't have a beta that writes y as a linear combination of columns of x, but we can find a projection of y onto this column space. And this is the best beta hat you can get. Right? So it's basically a linear algebra question to describe when can you make this loss 0. Okay. Right. So we have 3 different situations. So the training error will be 0. It's not 0 if d is less than n. If this vector beta is the dimension is smaller than the number of data you get, it's called the under parameterized regime. The training error will not be 0. And it will be 0 if d is greater than n. I can always find many solutions to satisfy this equation to make this loss 0. Actually, those solutions will live in a subspace from where our analysis in linear algebra. And you see there's a critical behavior at when d equals n. This is called the interpolation threshold. This is the case where you have enough freedom in those parameter beta to fully capture the training samples. You can make this loss 0, right? So this corresponds to the picture we have here. At some point, if the model becomes complex enough, you will have the training error get 0. This is the interpolation threshold. And from basic linear algebra, in this linear regression example, the interpolation threshold is about, is at d equals n. Okay. Any questions so far? So you can forget about this statistic question. Basically, it's a linear algebra problem to describe this interpolation. And then we want to ask, what's the performance on unknown data, right? So to fully explain what is the bias and variance of this situation of the test error, we need to have a definition in linear algebra that I will use later. So we have a low-rank decomposition of a symmetric matrix. If I know a matrix n by n, but it has rank R, you can write this matrix as a linear combination of eigenvalue lambda I and eigenvector ui transpose. This is a rank R decomposition of a matrix, symmetric matrix. And I want to take an inverse of this matrix. You know, it's not always possible. If R is equal to N, if the matrix is 4 rank, yes, I can take an inverse. Otherwise, there's an issue. The matrix is not invertible. But there's a general notion of inverse. It's called a pseudo-inverse, that you only take the inverse on those eigenvalues, non-zero eigenvalues. So we can define a pseudo-inverse of this symmetric matrix by still the rank R decomposition with the eigenvector ui, but then you take 1 over lambda I and ignore those 0 eigenvalues. So this is the definition of pseudo-inverse. Okay. Then with this notion of pseudo-inverse, we actually have a clean expression of the best solution in this training problem. So remind you that this training arrow is defined by the L2 distance between y and x beta, right? And we have 3 different situations, whether d less than n, d greater than n, and d equals n. When d equals n or when d less than n, we always have a unique solution. But when d is greater than n, there is a subset of beta that could make this arrow 0. Okay, so there are 3 different situations. But when you introduce this notion of pseudo-inverse, if we only care about the solution that has the minimum norm, L2 norm, that means even though I have a subset or subspace of solutions, if I pick the solution that's closest to the original point, so if the L2 norm is minimized, then we can find the best solution beta in terms of the training data x and y by using this pseudo-inverse operation. Okay, so this expression works for all cases of D and N. So this is the answer from training. You will get this best beta hat by minimize this the loss function, and this is the linear algebra expression. So that gives us a clean formula to analyze the training result. And we want to ask the test error, right? Yes, you are doing well on the data I give you, but I want to know what's the performance on the new data point. And the classical setting in statistics is how to evaluate this model. I can take a new data point, X, exactly from the previous distribution, like the data we get in the training set. So the new data has a similar distribution, the same distribution as the training data. And we want to test this, the model you get, beta hat, on this new data point. And the new data point is still from the linear model. So the X is the Gaussian vector, and the Y is the label of this X, which is given by the true coefficient beta 0 from the linear model, inner product with this X and plus this observation noise. Okay. So the goal is, can we recover this beta 0? The beta 0 is unknown to you, and you want to use data to recover beta 0. Okay. So when we define the test error, it is the difference between what you predict of this the label by using beta hat, which is depend on the training data, and what is the truth. The truth is that the new data point is from this linear model. So the difference between prediction and the truth is still a random variable, right? Because we are assuming everything is random. And when we take the expectation over the new data point and the model parameters, it gives you a number with a deterministic number, which we call it a test error. Okay, so this is the performance metric we want to do. We have a linear model, and I feed you with a new data point coming from this unknown linear function. Can you recover this label of this new point? With some linear algebra fact is actually the expected difference between this beta hat and the true coefficient beta 0. Okay, and we have you can plug in this expression, and do some linear algebra calculation, this gives you two terms, which has a bias and a variance. When we say bias, it is a term that does not depend on this noise epsilon. And the variance term will depend on the noise because the sigma square is the variance of the noise. So when you take sigma equals 0, that means without noise, then you only have the bias term. And there's a variance term that depends on the noise. Okay. So from this expression, you know, in the linear regression problem, if we ask the same question, I give you a lot of data, you train with the data, and you test the performance on the new unseen data point, you have a very precise expression of what's gonna be the answer, right? This test error in expectation, it has a bias and a variance term. Okay. But the key point here is the bias and variance are traces, right? A trace of some function. And trace of a matrix is the sum of eigenvalues. And you see what's involved in this trace computation is this sample covariance matrix, X transpose X. We didn't put the normalization, but you can divide it by 1/n. So here we find the conclusion is the test error is a function of eigenvalues of this sample covariance matrix. If we understand the distribution of this sample covariance matrix, which we had, which is the Marchenko-Pastel law, and essentially, we can express this test error as a function of the Marchenko-Pastel law. Okay. This is where random matrix is useful. So to make this random matrix to be relevant, we need to take limit, right? We are describing a high dimensional limit, and we need to make sure that the size of the data and the dimensional data goes to infinite at the same speed, a proportional limit with some gamma. And we can find the very precise limit for this bias term and variance term. This bias term basically from the rank of a random matrix, so it's actually quite easy to compute. And the variance term calculation depends on you take some test function and use the convergence result of Marchenko-Pastel law distribution, you get this variance expression. So the calculation of this limit of the variance relies on the Marchenko-Pastel law. Okay, I'm skipping a lot of details to derive it, but you can believe me, if you have the limit of sample covariance matrix eigenvalue, you can compute this because it's a function of eigenvalues, which we saw on the previous page. And by adding this bias and variance, you get expression for the generalization error. Okay, it depends on the noise of the observation, so that you have a sigma square variance term, and depends on this aspect ratio, the ratio between D and N. And here is a plot that you can draw from simulations by taking different, so the different color of the curve correspond to different variance. Okay, so the variance will make a difference for the performance of this linear regression problem. Okay. Also, what's important is this gamma, the proportional limit. So the ratio between dimension of the vector and the size of the sample also makes a difference. And you see there's an interesting picture, right? Gamma equals 1 corresponds to this interpolation threshold where your model is big enough to fit all the data. But the generalization error gives you a non-monotone behavior. When gamma is small, the error goes up and you get a peak. And after you pass through the interpolation point, you go down again, and later on it goes up. Right? So this is already very similar to what we see in this experiment data example, where you have some non-monotone behavior, right? You go up at some interpolation threshold, and you go down. But it's slightly different because here you have a U shape, and in this linear model, it doesn't have a the first descent. In the first curve, it just goes up without going down. Okay. And we actually have a pretty intuitive explanation of what's happening when gamma equals 1. So you see this error goes to infinite, right? If you just take gamma goes to 1, and it goes down. And this is the situation when the matrix is perfectly square. If you have an n by n matrix, and this has something to do with the condition number of this matrix. When the matrix is not exactly square, the largest singular value and the smallest singular value stay bounded. And that's correspond to the stable curve, the curve that has the finite value. But when gamma is approaching 1, it's a situation where this matrix becomes perfectly square. And in this case, the matrix is very unstable because the largest singular value and the smallest singular value, the ratio blows up, goes to infinite. So that's correspond to this peak situation. But you see, this model is not close enough to neural network because we only have a linear function with some coefficient, and the only parameter we are tuning is the ratio between d and n, right? So this is not rich enough to explain neural network, but it tells you you could have this non-monotone behavior even by looking at linear regression, some classical regression task you will learn in basic statistics. And the key difference between what we learn in classical statistics is that it is a high-dimensional phenomenon, right? We are taking d and n both goes to infinite. That's not a classical thing you learn in standard statistics class. Okay, so this is one step. We understand linear regression in simple models.
I have a question. So what does it tell about? What does it tell us for applications? I mean, what gamma should we take? Or are there any practical, conclusions of that, of this graph, you know? Did the end
Yes.
is big when we have square metrics?
Yes.
And it's small when we have small gamma, or it's not that high when we have large gamma?
Yes. So
practical conclusions for
yes,
application?
very interesting question. I think the goal for this model is just to show you that this is not a specific phenomenon for neural network. You can see it in linear regression, but there's no model parameter you can tune. That's the question you asked, right? Because we don't have a very rich function class. Basically, it's a linear model. And d and n are given to you because once I observe the data set, I know the dimension of each vector. I know the size of the data. So there's no parameter you can choose. And this just explains that you will see a non-monotone phenomenon by applying linear regression to this model problem. And later there are more closely related to neural network problem I will explain. But this is the first step. There's no parameter you can choose. Is that clear?
Okay.
So mostly it's explaining the phenomenon, but there's no practice so far because this is a classical procedure. You follow the recipe, you get this phenomenon, nothing you can choose. Right, this is saying for linear regression in high dimension, you could have this arrow goes up and down. Okay, but let's get, we have more examples built on this intuition, we'll see. So the next example is relevant. How do we go beyond a linear model? So now we can study a very simple neural network with random weight, where here you can choose parameters. Okay, so what is the neural network? It's a two-layer neural network with n neurons. So this Wi could be, you remember we have vector and you pass through some edges. And then in the next layer, you have a different collection of points. And that's called a neuron. So when we have a d-dimensional vector, you can take n neurons. That means I take n different weights to take the inner product between this weight and the vector. And overall, you have n such neurons. And after you pass through the first layer, and you take those thetas, you take a weighted sum of these neurons, and you normalize. This is the function of a two-layer neural network. Okay. Now you have a freedom to choose how many neurons I have, right? Basically, how many nodes I need to take, how many weights I want to put on the neural network. And there are two collection of parameter. So this Wi is the edge weight, right? It is a dimension, it's a matrix. If you put all the W together, it's a N, capital N by D matrix. And there's other coefficient theta I, where we aggregate all the neurons to a single number. So you start from a vector X, multiplied by this weight matrix, and you take the weighted sum of those computation, that's output a number. So the theta I gives you this combination of these neurons. And there's one simple model you can ask is, since there are so many parameters, let's just make it random. Let's hope this random parameter give us still some information, some useful property. So we just take the weight matrix to be random matrix, where every entry is independent Gaussian entries. And now we keep this W random, but then we can define the optimization problem to train the output layer. So the theta I, there are n parameter theta I can define a loss function to minimize this theta I. This is called a random neural network, but with the output layer trained. How do we train this layer? We define certain loss that depends on this parameter theta. This is basically the error you make on your training samples. And there's a penalty term that's called a reach regularization, which encourage you to find the parameter theta with a small Euclidean norm, small L2 norm. Okay, so you can define some optimization procedure to minimize this function and find the best theta, right? Where just take the random weight untouched, but you do optimization to find the best theta. Okay, and there is explicit expression to compute the minimum minimizer of this loss function. You get a theta hat. Okay, and you plug in this theta hat here to make this F your neural network, right? So your data comes in, it's mapped by some random vector, and you pass to a nonlinear function. Afterward, this theta I is carefully chosen to give you the final output. So there's some random part, and there's some part of theta I that depends on the data. Okay, so this is a simpler model called a random or two-layer random neural network. Okay, the key feature here is because this loss function has some very nice structure, you can still have explicit formula for theta hat. So you can still understand this partially random neural network. And there is this informal statement about a rigorous result obtained by May and Montanari in 2022. If you assume instead this weight, instead of Gaussian, you assume they are uniformly distributed on the unit sphere, d-dimensional sphere. You can always do that by normalize the weight. Like you normalize the Gaussian vector, it could be a uniform vector on the sphere. And we also assume the data is some uniform vector on the sphere. And the label is given by some unknown beta inner product with this data vector. Okay. And now we have three different dimensions, right? N is the number of your data set, and D is the dimension of this data vector, the dimension of the sphere, and capital N is how many neurons you are choosing, right? How wide this neural network is. It is. We're fixing the depth, so it's just two layer, but I can choose how many neurons I have. Right? This capital N is a parameter you are free to choose. Okay, and in this case, you can still rigorously compute the limit of the generating error, but it all becomes more complicated. It depends on this lambda, which is this regularization parameter we choose, which is like the parameter that you encourage to find a smaller norm, theta. And the psi1, psi2 is this 2 aspect ratio of the ratio between number of neurons and dimension and the size. And it depends on other model parameter because we have a activation function. Theta is activation function. So this final limit will also depend on some derivative of this activation function. And here is the curve. So this curve has the x-axis depends on the ratio of neuron and the data, right? Psi1 divided by psi2 is when you do the ratio, this little, sorry, this is a typo. This is the little n. So capital N divided by little n is psi1 over psi2. So
the statement of this theorem mainly concentrates on the fact that the limit exists, yes?
Yeah, the limit exists, yes.
Okay.
And this is the curve you draw from this prediction. So this curve are the when you change the ratio of psi1 over psi2, you get this curve from the limit. But the expression is so complicated, you need to have several equations to describe it. So I just give you the plot. And this is a ratio about how complex the model is, right? Because the number of neuron is what you can choose. And if your n is larger and larger, the model is more complex. And this is a parameter you can tune. And there is also this interpolation point where capital N and little n is proportional. So this is the place where you see the peak. And you have this U shape in the first stage. When the model is not complex enough, the generalization error goes down and up. And after the model gets more and more complex, it goes down and down, and it's stabilized at some point. It has a limit. Okay. And see, there is this proportional limit. After a very difficult calculation in the many random matrix estimate, essentially this curve comes from a transformation of Marchenko-Pastel law again, but it is more difficult to derive. And the reason you get a Marchenko-Pastel law behavior is still that we have a proportional limit and the data is random, the weight is also random. So expect in a very large system, if the dimension of the system goes to infinite at a proportional rate, you will expect some random matrix behavior. And this is close enough to describe the empirical phenomena in neural network with a very tight model. Okay. And
your time is almost, well, it's up, in fact. So you still have 3 slides, so maybe you can just go fast through them.
Okay, yes. After that, there's no theorem. I just give you some simulations. Yeah. Okay. So the new challenge here is it's a random matrix model, but we have some nonlinear function involved. So it's besides the random matrix problem, it has some nonlinear feature where it's not covered by the standard Wigner matrix model and sample covariance matrix. Okay. And there's another interesting phenomenon called multiple descent. It says you fix this architecture of a neural network, but you increase the number of data points. So imagine L equals 1 means the number of data and the dimension is proportional. And L equals 2 means the data, you have more data. The N is about D squared. You have a larger magnitude of data and so on. So for each L, you have a different peak. So the arrow goes up and down and up and down and up and down, but eventually it goes down, right? When you change the ratio, it has some non-monotone behavior, but after you pass if you increase the number of data points by a bigger magnitude, it eventually goes down. This is called a multiple descent phenomenon observed by in neural network, and it actually can also be proved in some situations by using random matrix tool. So this is some recent development. When people study random matrix in this polynomial proportional regime, not a linear proportional, but n is proportional to some polynomial. And my self field is very interesting because it aligns with some phenomenon we see in large language model, where you just keep feeding the model with more data point, and eventually it always gets better. So the model always gets smarter and smarter if you see more data point. So this is some random matrix toy model. You can explain this phenomenon. Okay, so let me just conclude. What we have discussed today is that in some simplified model where the weights are random, the theoretical analysis of the behavior of neural network is closely related to random matrix theory. If we make this model nonlinear, it requires some understanding of nonlinear matrix model, which is some very active and recent area in random matrix theory. But in reality, when we train the model parameters, the weights will not be purely random. It depends on the data. So there's still active research going on to study how these weights actually change during the training, and how this neural network weights really learn the property, the feature of the data. So there are experimental results that in some architecture of neural network, if you look at the weight matrix, it contains some information of the data. So they are not purely random. The power lies in that you learn some feature of the data in this weight. So this is the image task. When you pass the image to different layers, the first few layers could just learn some background information, and maybe the second layer learns some a boundary of your face, and then you have more detail for the face. So this is some phenomenon that's not explained by what I just described. But there are some new results still using random history with some optimization procedure, trying to explain what neural networks learned in the weight. And you can see there are still a big and growing gaps between theory and practice. One thing that theory development is very slow, where we have to make very specific distribution assumption of the weight and take proportional limit. And there are some assumption you need to make on the activation function. To state a rigorous result, you need like 10 assumptions. But in practice, it just always works. And every few months, there are new architectures appear that grows, have a much better performance. So there's a huge and growing gap between what theory can prove and what we see in practice. But on the other hand, it gives you many open problems that you can think about and many inspirations for mathematicians. Right? For example, random theory, you can see, oh, the nonlinear function should play an important role. So we should be able to study more about this nonlinear effect in random matrix model. So this is some new phenomenon that excited to explore. So now I want to list some relevant literature if you want to know more about this area. So there's the classical book of spatial analysis of random theory, and there are some recent survey papers and important results talking about this double descent curve and the generalization error in neural networks. Thank you for your attention.
Thank you. Well, thank you very much for your illuminating lecture. Are there any questions? Comments, please?
I want to go back to double descent phenomena. You mentioned, yes, that like
Here or
you have
here?
like the best no, it was earlier, somewhere on the first part.
Here?
Yes, is this that picture? Next slide.
Yes.
Yes, this picture. That like classic regime that you can find like the proper amount of parameters between your model being under-parameterized and over-parameterized, and like there is modern regimes that if you over-parameterize your model and you add like very, very, very many parameters, the risk will go like to its minimum or something like this. And I'm wondering, is this modern approach like already used, or it just stays somewhere on theoretical part and all of those neural networks are still working in classical regime?
And so now the common belief is, yeah, we are entering the modern regime. But one caveat here is this curve does not go to 0, right? It will be flat at some point. So neural network cannot just learn everything. It has some limitation. So there is some new limit theory called the scaling law of neural network. It says if you have lots of computation, lots of data, and how many parameters, you have asymptotic prediction of how this arrow will go eventually, but they will not go to 0. But the situation is that we are in this more modern regime when you talk about over-parameterization. And I think this is commonly observed. But this is not monotone. It's just a picture, a conceptual diagram, but it's not a precise description. Is that your question?
Okay, mostly. I got that it doesn't tend to 0. I was just wondering, is it used somewhere practically now to like develop some neural networks, or still like practical side stays on classical regime?
Oh, yeah, in practice that when you see some non-monotone behavior, you should not be afraid. That's one message you can learn from this analysis. You can still increase the model parameter and eventually it will get better. That's something you can learn from this. And that's how this language model is developed, right? They just keep making the model more complicated and eventually gets better. So this is consistent with what theory predict. But to really guide you how to train a neural network, it is a problem about optimization. And this is something I didn't talk about today, right? You need to have define a properly defined gradient descent procedure and take how to take the learning rate, how to choose those parameters. There are guidance from mathematics and probability statistics, but it's more complicated to describe. And it's an active area to guidance the practice.
Okay, thank you.
Are there any other questions? Yes, please.
Yes, I have the following question. Is it possible to give some example, one at least, of some phenomenon which one encounters in this context of deep learning, which was easier to understand looking on a purely infinite dimensional case, and then somehow going down to the finite but very large dimension?
Yes, there is a successful theory called the neurotangent kernel, because this is something we also see in the classical something called kernel regression or kernel regime, is that when you take infinite limit, this neural network could behave like an operator in infinite dimension. And there's a theory called the neurotangent kernel theory, which says when you take the width of the neural network to infinite, you can describe the neural network behavior as a Gaussian process, and it has a precise analytic behavior. And then you can ask how big is the network width has to be that you enter this infinite width limit. And so that also has something relevant to random matrix theory, actually, how the kernel matrix is concentrated to its expectation. So yes, so there is some methodology that you first take the width to limit, and you understand in the infinite limit case, and then you see what's the correction I need to make between finite width to the infinite width. Yes, that's one popular approach, actually. Actually, some of the results can be, for example, this curve, you can also take capital N goes to infinite. There's a different theory to describe this double descent curve. You can also see it in infinite width neural network.
Okay, great. Thank you.
Okay. Are there any other questions from people on Zoom? Any questions or comments?
I think that there is one question on the chat.
Anna?
No. So maybe repeat this question. So it is interesting to consider when this dn are not proportional, but this ratio tends to infinity. Is it also interesting? Yeah. Not machine capacitor, really. Yeah. Is it interesting?
This is still a machine capacitor. So
okay, this is
yeah,
still...
it is still
No.
machine capacitor, and the reason why you have this proportional limit is somehow related to this random tensor model that some random matrix people studied in quantum information theory. When you take a when you take a vector and you tensor the vector to some power, then the vector lives in a dimension d to some power. And when you take the proportional ratio of the tensor vector, this is relevant to d over d to the L to some constant. And in this random tensor vector model, there is Mashenko-Pascal law. So
yes, I know. I worked with this model, so really, yeah, we have really. Yeah. It's still marching capacitor. Yeah.
Yeah, but it takes several steps to translate that problem to this neural network. In this paper, they basically see an analog between random tensor model and this polynomial scaling limit.
And L here is what L? This parameter L is this tensor model parameter L.
Yeah, you should tensor the vector.
Okay, this from tensor. Oh, now I understand. Thank you.
Yes.
Okay. There is also a question on chat. Is the theory applicable to biological systems like the human brain?
I think there's this random feature model has some connection to a biological network. But I'm not an expert of this. I don't learn any like concrete applications in biological model. But I think that there are a neural network model to describe like a brain structure. It's similar to this composition of weights and nonlinear functions. Some perceptual model that people study. But the limitation of this random probability analysis is you are taking weight to be random. So the active research still go to get rid of the random assumption and really understand what's the weight, the behavior of the weight after the optimization step. And there are some progress. For example, in the very last, in this paper, this group of researchers, they study how this gradient descent step can influence the weight in this random matrix. You start with random initialization and you take a optimization step, and they have a connection to a spike matrix model after the gradient descent. Basically, you see the eigenvalue distribution, and there are many outliers. And the outlier eigenvector contains information of the data. So there are some attempts to go beyond this purely random weight. And that's very interesting because also we have a spike matrix model case in random matrix theory, which talk about information plus noise, how the behavior of the matrix is. So that's something relevant.
Okay, thank you very much. Let's thank the speaker again.
Thank you for your attention.
Thank you very much. Okay, so we terminate our session.